I wanted to talk with you about a project that we use the VE Pro tool on. We've been VE users for several years, and it's a primary tool for building analytical modeling in our office. This building is at the Colorado State University campus in Fort Collins, Colorado, and it's known as the Engineering 2 building. It has a bioengineering research facility, a classroom, and also a data center. And we've been working with this project since the beginning of programming even. Most of this work occurred in 2011 that I'll be showing you today, and that is the analysis that we have. So this view of the building is a view from the northwest. The building is on the north edge of the campus, and it has a basement mechanical system, and it also has a penthouse, which is the top block on the roof that's closest to us, where air comes into the building and is pre-treated. Just to the south of that, you can see the exhaust for the fume hoods for the building. And also located in that data center, or in that penthouse, is a data center. And I wanted to also point out between the two bars of the building is the atrium. It's covered a little bit in this view by the roof. That rooftop geography is very important to the project. There's a lot going on in that. There's also smoke exhaust for the atrium located there, and around the atrium under that roof is a clear story on the south, east, and west of that. And I wanted to point that out just so that you get a feel for what the building is on the exterior as we move on to take a look inside. All right, so taking a look inside the building, you can see the typical floor plate. This south bar has the administrative offices, the classrooms, and the grad students. The atrium there in the middle, and at the top, the north part, is the research space, the laboratory space. So most of our analysis that we're going to show here today is focused on this atrium, and we're mostly going to be viewing it from the east direction or from the right-hand side of this picture. And the atrium is an interesting space for this building. It's going to have 24/7 potential occupancy as grad students come and go to do their studies and to take care of the research projects. And it's meant to feel comfortable and homey, to be that home away from home for these students. And while the mechanical equipment and the other technologies that are built into the building won't be accessible to the people accessing the building on a day-to-day basis, the experience of a low-carbon, high-efficient, well-performing building is really meant to be direct in the atrium itself, at a place to experience views and daylight and also natural ventilation in a very comfortable space. So moving on to what the atrium is going to look like in a rendering. This rendering is courtesy of Slater Paul Architects and their partner Ratio Architects. And you can see this is a view from the east, and we're looking up towards the grand staircase, so you can see the main level and then two more levels where building occupants are going to have access in the atrium. And you can see that clear story in some of the daylight features that are around the space. So here's some of the daylight analysis that we did. This is early in schematic design, and we were doing a proof of concept. This is definitely a facilities staff that is very involved in the design of their facilities. And I think, this is my words, not there, but they live by the mantra of sustainable means it's also maintainable. So one of the things that we were doing with this daylight analysis was not only to get a feel for what it would look like, but to test proof of concepts of skylights versus tubular daylight devices, make sure that it had the architectural treatment that we wanted, and also to address potential maintenance concerns for the amount of roof penetrations and the potential for people inside the space to see debris on the roof, or whether it would create another requirement for maintenance on the roof that was not desired. As it was, we went with the skylight scenario, which is the image on the left-hand side, which was shown to have better daylight performance overall. So moving on into the natural ventilation portion of our analysis, we looked at the wind resource. Looking here at the wind rows, you can see that the wind direction comes from a variety of directions, and that we were going to be using buoyancy predominantly rather than wind-driven data. And obviously, anyone who has looked in these data sets knows that the trick is to find wind data that is relevant for your site, and we worked awfully hard to do that. We ended up using the TMY3 data for Fort Collins, thinking that that was representative, especially since the project was going to be more of a buoyancy than wind-driven natural ventilation type project. So here is a picture as our building was imported from Revit, and I wanted to point out that this was a perfect import. When the architects understood the small addition in steps required to have a good GBXML transport into IESVE, they were able to easily incorporate those steps, and we had a completely successful import into IESVE, which shows that it's very attainable to do this process with the BIM benefits for all of us. The areas that are circled are the operable window openings. So we have operable windows on the first floor and also at the very top of the atrium on both the east and the west side of the building. And we were looking at the amount of area for those operable windows compared to the air movement that would be available. So looking at some of the MacroFlow results, we were looking at the bulk airflow movement driven by either wind or by buoyancy-induced pressures. And the east-west opening showed the results that we were hoping to see, that we did get a buoyancy-driven wind effect that was very effective. So we did not have any fan assistance for these results. So we varied the total free opening until we found one that was appropriate for both the natural ventilation and for the architecture. And here's a look at what the passive cooling results would be. This is using a sequence of operations where we're looking for a comfort range in that atrium between 68 degrees and 77 degrees. And any time that the atrium would be 73 degrees or greater and the outside air would be 50 degrees to 73 degrees, we would allow the natural ventilation to happen. So you can see that we're getting a cooling effect through natural ventilation from March through October, that these effects are available and that folks in the atrium space would be able to participate in that. We wanted to check the proof of concept further, and we wanted to look at temperatures and comfort further. And this is a plot of some VE Pro data where we're looking at the temperatures on the first floor as well as the third floor. As you remember from the rendering, that grand staircase has the potential for people being up on the third floor, and we wanted to make sure that they are still comfortable. So you can see here the temperatures varying through the day during the month of June, and that the red line, the third floor line, is higher than the green first floor line, with a maximum of 78 degrees, which we felt was appropriate for a proof of concept and still being inside that comfort range. And here is what the amount of air looks like for that same time period in June. And when the strategy is on, we're getting ventilation rates of between 12,000 and 14,000 CFM. And these results were very helpful for Colorado State University to say yes to moving forward with this strategy, which we are just delighted in. So they were going to have the operable windows on the automatic controls for the atrium space. And with that, we switched our thoughts a little bit to how will the air move inside the atrium, not just a matter of the mechanics of the windows and providing the right control for the windows, but to look at the airflow itself. And here you can see our first round of results where we're now using the MacroFlow tool, so computational fluid dynamics, where we're looking at the airflow through the atrium space. And we've added CFD people here to be representative of the occupants that will be in that lobby space. So they have a heating component to them. They have a 200 BTU sensible component as well as a latent component. And the important thing here is that the air coming through the east and west openings is indeed getting to where the people are there on the first floor so the people can breathe. And this was a very nice visual result for us to have as, again, proof of concept. And we used the MacroFlow results to have the boundary conditions in this MicroFlow CFD model. And I think it's always a challenge to simplify the model so that we can run it in computational fluid dynamics and still have the appropriate look at reality. And here we tried to balance it. You'll see that that staircase element, for instance, has been removed since we thought it wasn't especially material to the problem at hand. Now, I had mentioned back on the very first slide, if you remember, the exterior of the building, that there's a lot happening on the roof of the atrium. There are smoke exhaust fans sitting on the roof of the atrium, and we wondered if there would be a benefit to having the smoke exhaust fans contribute and open up the number of hours that the natural ventilation or the openings could be available and have a fan-assisted way of delivering air to the space. And so the second part of this was to test a second option where the smoke exhaust fans were used in the atrium space. And as you can see, the air comes in through the side but exits through the roof and is not very present where the people are. So this helped us to go back to the first option without the fan assistance for the appropriate natural ventilation strategy. And with that, that concludes that look at daylight and natural ventilation for the Colorado State University Engineering 2 building.